Okay, I'll go ahead and get started. So this talk today is about leveraging robot data in autonomous vehicle development. So I work at a startup called Zoox. We are building autonomous vehicles. And I'll talk a little bit today about some of the ways that we use the data that we collect on the vehicle to sort of improve our development process and sort of inform what we do. So robots, autonomous vehicles are robots, and Zoox is building. I don't know if you know our mission, but Zoox is building. Our mission is to deliver mobility to the world, to dense urban environments, and our goal is to build kind of a full stack, a full solution. So we are building the vehicles, we are building the AI software which is going to drive the vehicles, and we are going to own the fleet that we build, and we are going to operate the fleet like a taxi service, robo-taxi, so the whole stack. And that gives us some big advantages that we think are important as compared to some of the other companies that are effectively just tacking on robotics to existing cars, because those cars were designed to be driven by humans, and if you throw the robot in there trying to drive it, there's a lot of things that don't work as well. And if you build the vehicle from the ground up to do it right, then we can do a better job, we think. And so during our development process, we're kind of working on two forks at the same time, or two main prongs of development work. And one of them is we're building the vehicle, which is, we have some prototypes. Actually, some of those cars in the video this morning were our cars driving out on the Alameda track. They look like dune buggies. So those are our prototypes for the actual physical car design. But most of the work we have, the hardest part of the problem is developing the AI software for actually driving. And that we do with what are known as level 3 vehicles. So I don't know if you're familiar with DOT autonomous levels, but up, 1, 2, 3 are the levels where humans are involved and at some point in like driving the car. So level 3 is a car that's mostly autonomous, but the human doing a backup. So that's what we have here, and this is what most of the other autonomous vehicle companies use for their sort of driving model and training model. So there's a trained driver in the driver's seat, and a software operator. In our case, we always have a second software operator in the passenger seat, taking notes and watching out for certain things. And then at some point, when our level 5 vehicles are done and our software is done, then we'll put them together and be out in the public road someday soon. So robots are like frogs, or like any other animal. If you think of them like that, is that they have sensors or senses, like cameras, LiDAR, radar, time of flight, sonar. Some autonomous vehicle companies that are making autonomous autopilot cars are sort of betting everything on the camera, and in theory, humans can see and we can drive, so therefore a car should be able to drive if it can see. But the compute power that our brains have compared to what we have even in a stack of GPUs is vastly different. So in order to kind of hedge those limitations and bring in multiple modalities of LiDAR, radar, time of flight, sonar, other sensors for short range, we can get a lot of sort of cross-reference information and a lot of reliable input about the environment that you wouldn't normally have with just cameras. And then the compute, so the robots have compute, and we use CPU and GPU. A lot of the work, especially with like vision and perception processing, can be done on GPU. It's much more efficient for doing machine learning and that kind of processing. And then whenever decisions are made about what to do, those signals go back out and control motors and actuators and speed controls and all sorts of hardware. And so every car today has buses all over it, right? So CAN bus, LIN bus, there's a bunch of different kinds of just normal interconnect on your car that sends signals between sensors and little actuators and controllers for all different parts of the car. So our vehicle is similar. So we have a lot of the standard car buses that we're dealing with at the low level for physical control of things. But we also have some higher level buses, because you're not going to run LiDAR stream of data and camera streams of data over a CAN bus. So we also have Ethernet buses and and other kinds of routing, switching, kind of more like a whole compute. It's like a tiny data center stuffed in that car. So that brings all of the information into the central computer, or we call it the PCU, which is sort of controls it's the main brain of the car. And then within the main brain are dedicated processes. So it's an interesting architecture. I found it fascinating when I joined, in that there's effectively a high-speed message bus that runs on this machine, which is a multi-core, multi-processor machine. But the message bus then allows different processes or components, software components, to publish and subscribe. So pub/sub, but at a very high speed. And the messages go across the bus, and they have intended recipients who can read the messages back. They all do their own part, processing images, doing detection, doing classifications, building 3D model of the world in real time and maintaining that model as the vehicle moves. Localization, like all sorts of decision making, planning the robot behavior. So we have a lot of data. And what should we do with it? So let's capture it somehow. Now, in a traditional kind of server environment, you often end up doing like log collection. So you'll have your servers are writing maybe just standard out, and it's just dumps, and you're trying to write filter scripts or pattern matching to pull out interesting logs and route them through your log stack. Or maybe your servers are better, or your systems are better, and they're writing JSON, and that's really nice because it's much easier to parse and you know what you have. But typically it's a little bit fuzzy, and you're trying to extract the nuggets out of the stream of text, raw text, just line by line. But what we have is a bit different, because what went over the bus in our system are actually different kinds of structured messages. Most of them are protocol buffers. I don't know if you're familiar with Google protobufs. Some of them are ROS messages from older ROS-based open source platform that we use. And we also use DDS messages, which are a standard from OMG DDS. So those different kinds of systems use different messages, kind of depending on where they came from and what they're being used for. So in a lot of ways, like taking these messages that are just literally already sort of compact and concise and already self-contained and parsable, we can just write them to disk in some kind of format, and we already know how to deal with them then. We don't have to try to parse them. We're just recording. So at this point, our recording is more like a flight recorder in an airplane. So we have to kind of control when we want to record. We don't really want to be recording all the time when the car is driving. So we have, as part of the software operator workflow and the team that's going in there to go out on a mission and do a drive, they will control the setup of what software components are going to launch for that drive when they start recording. And then during the recording, the operators will be taking notes and maybe signaling that something went wrong and writing up a little write-up about it. So all that information can be then packed into the messages and recorded and saved. So they're also controlling the recording. So when we begin, when we end of the recording. So that's important. So let me show a bit of a scene here. So this is what the operators see when they are driving. Well, not the driver, but the software operator. And you can see they're turning on different things. So they turn on LiDAR, turn off LiDAR, the planner information. So all of this is sort of a visualization for them to see what the vehicle, or what the planner, what all the components in the AI components are actually doing and thinking. So this is sort of it's a visualization of the messages themselves. So the operators can turn them on and off because they don't always have to see everything. Usually they don't need to see the LiDAR, but they mostly want to see what the vehicle's planning on doing. But we record everything. So all of the data that's going across the bus will be recorded, regardless of what they do with the UI. These are really fun to watch. I don't know. Yeah, you can see like the little flags with the letters like C081. So those are other agents in the scene. and we label them other cars or are they pedestrians, and it also shows the modality that they're sensed in. So vision, LiDAR, radar, oftentimes we'll pick them up with 2 or 3. But you can see in the case where we see things with only one modality, it's like, well, that's a good case for, it's a good thing we have more than one that we're looking for things. If we were just relying on camera, there were a lot of things we wouldn't pick up that we were able to see with the other modalities. So what is it that we are collecting? So all the messages go across the bus. We don't collect absolutely every message because some of them are really big. But we do capture most of them. The main thing is that when we capture interesting decisions and lower bandwidth kinds of perception information, so localization, 3D model, prediction planning, all those are very important messages. They're not particularly huge. We capture all of that. Sensor input, we do reduce it a little bit spatially and temporally. Like for the camera data, we're capturing stills, but we also capture video flow, but we compress it, H.265, because it's just too big to record raw video from 16 cameras. That's just a lot of data. But actuator control, other metadata like maps and routes, where did the vehicle go, what map was it using, what did the operators do, what mode were they in, what switches did they have on and off, all of that we can collect. So we have a lot of data that's flowing. We're collecting it in process from the bus. In theory, you could try to transmit it up over LTE to the back end. That would be kind of cool if we had that kind of bandwidth, but in practice, we don't. So we write it to disk locally, and we'll drive around collecting all the data, so on the runs. And when the mission is done, we'll take it back to our base station and upload it somehow. So then how do we want to do that? And in what format should we record it? So on the vehicle, we're writing disk. We originally used, because we started out using some of the open source framework called ROS, which is Robot Operating System. We used a native format that they had called bag files, which are kind of an indexed database file that you can write messages to, which is pretty handy. A lot of tools work really well with it. But it tends to write everything into one file. And the index is sort of built afterwards, after the fact. So when we're writing, if we decide we want to be able to do 4-hour missions and driving for, you get up to like almost a terabyte of data after driving that much. Those files are so big and just completely unwieldy and unusable. Once we try to port them back to the back end, if you copying and dealing with files of that size, it just was really a problem. So we changed the way we recorded, and we took advantage of some of the basic nature of how the messages are. So the messages all have types. So they're like protobufs have types. We know the type information for each message. And they're also published on topics. So like a typical message bus, there's a topic that is sort of the label of what the stream of messages are all about. And so those topics are named nicely. And then they all have timestamps. So we have a very accurate clock. We can time. We know when the messages are being published and they're being written to the disk. So we can timestamp and make use of that as a way of organizing it. So what we did is invented our own format that we call CHUM. So it stands for chunked messages. It's a funny name. Some people really hate it, but it's funny. It get caught on. So the idea, I think of it like a strip recorder. If you've ever seen those old school with all the pens that are kind of wiggling and writing on the paper, it's sort of the same thing. So each topic is being written in its own file, and at the end of every minute, we close the file, flush it, and then start the next file in the next directory. So there's a directory tree full of files at the leaf, and the directories are all based on time, and then the files are the topics for that 1 minute window. So you have this 1 minute that you're writing the topics, and then the window closes, you'll write, and then move on to the next one. So the intersection of a topic and a minute gives you a chunk. So it works really well because we can write continuously. And in theory, you could be writing and uploading the data from an hour ago at the same time you're writing new data. We don't actually do that in practice, but in theory, we could do that because it's just sort of this continuous flow of writing. So we did invent this. So this is something that is our own proprietary thing, but we built it on top of open source lower level libraries because we don't want to reinvent everything all the way down. So we built it on top of the SSTs, the SS table, sorted string tables that are kind of the low level storage chunk platform that the Google's LevelDB database builds on top of. And it works really well because SSTs are used in this kind of a database as an append-only mode, kind of write system. So you're writing to the end, you're writing to the end. And then those little immutable written sequences are then wrapped up and read from an in-memory database, in effect. So we use the same thing, but we write the records as just two fields. The timestamp in nanoseconds, when was this record written? And then the message itself is the rest of the payload with a little bit of metadata to describe what type was this message, is there any extra little data that needed to go with it, kind of metadata for the message that maybe came over the bus that wasn't in the message, but it was sort of about the message. Things like the published time versus the written time, a few other things like that. We can always add more extra data as we need to. That's sort of out of band from the actual message. So then we need to get the data into the system, into our systems. So the data's on the car, and we want to get it into the cloud. And in our case, cloud is AWS and on-prem, our own data centers. So it's a mix. And we move stuff around just depending on what makes sense for performance and cost and latency to the systems that are going to need the data. So, but initially, like S3 is a really great storage system. We like it. And so that's our main sort of hosting place where things go. So what we like to do is take the runs that were created by driving, upload them, get them into the cloud, kind of get them cataloged, and a little bit of metadata pulled out about what happened, when was the run, who was on the run, what vehicle was it on, and sort of get that little database built, that sort of sideband to the chum storage itself. But there's some challenges in getting that much data up. It's often really spiky. Our teams drive around during the day. Some days are really busy. We're doing a lot of driving. They all will tend to get back to the base station similar times, and they want to turn around and get out again. And so you'll see these big spikes where everybody shows up. We want to get the data off and then move on. Other days are not nearly as busy. And this was like a year ago. Now we do a lot more driving now than we did a year ago, but even then there was big spikes. So there's kind of a demand to get the data off the vehicle, get the vehicle back out again really quickly. So we tried a few different things. The vehicles are running basically like a small server rack of compute, and it has a bunch of SSDs in there. So they're just regular SATA drives we can plug in. That's our storage. It works really well. The bandwidth writing to a big RAID array of SSDs is really good. That's a straightforward problem. It's also like interesting thing to think about. Maybe we can just plug in the Ethernet and upload everything. That in theory should work. But in practice, if you've got a bunch of vehicles waiting, trying to upload a terabyte of data over even a 10 gig Ethernet, that starts to take a while because you're not ever going to get 100% efficiency, and there's going to be something upstream that slows everything down. So the 10 gig Ethernet ends up being kind of our backup plan if something's going wrong with the drives, or if they don't need the vehicle right away, we'll sometimes use the 10 gig. But so using the SSDs themselves was great. We have kiosks that we set up at the base stations, which are just very simple Linux boxes that just have drive bays, auto mount the drives, look at what's on them, upload them, clean them up. So basically doing a safe move into the cloud. And so it's just sort of a dumb machine that's pumping the data up into the cloud. Works pretty well. But there's a few things can go wrong. I think the most likely thing that goes wrong is the physical connection of those drives in and out of those drive bays. They're really not made for that. They start to wear out, the pins bend, they don't seat all the way. So people plug them in and walk away, and nothing will happen. Or they'll get unmounted, they may be not cleanly unmounted, and they're pulled, and then some of the boot information's corrupted on them, and they seem okay, but they don't work. there's lots of things going on. So there's a lot of like operator and sort of runbook stuff that has to happen where people know, okay, it did this, you know, how do we address these things? And then the other one too, the network could go down and now we're stuck. Or we're just clogged up with so many uploads going on at once that everybody's blocked up waiting. And that usually happens when all the people that know what's going on are on vacation and I'm the one in charge and I'm on pager and like, oh, what's going on? I got to figure it out. So that's, of course, that's fine. So that does happen occasionally. So we tried to find other solutions, right? How do you mitigate the problem of just dealing with plugging these SATA drives in all the time? And our current solution that's working really well, USB 3.1 drives. These have really good bandwidth. We can write everything we need to onto one drive instead of having 8 drives. They're rugged and the connectors don't wear out nearly as fast as the SATA pins. So this has really been a big boon to our reliability of getting the disks uploaded and without a lot of human intervention, right? Things will tend to just work. And we still have the network if we need to. So once we upload the data, we have back-end systems that will sort of scan the chum and look at what was there, look at the metadata, and then catalog that up and break it up into runs, that we call them. So every sequence of recording, when the operators got in and turned it on and we were recording data, we call that a run. So beginning to end, that's a run. It had a purpose, it had a driver, alpha, so all the metadata about that. So we catalog all those. And for each one, we can extract a bunch of metadata. So we look at everything that's sort of related to the, let me try my little pointer. Ooh, yeah, okay, look at that. The metadata for the run, it tells you everything about the run, the time and what mode it was in and the vehicle and the purpose of the run and where it currently is in the process of going through the pipeline of work. And we draw a little picture to show where it was, where it happened. So this is like 5 blocks from here. This is where we mostly drive, up off Broadway and up north from there. We also scan for, this is still working pretty good, incidents that happen. So some messages will contain metadata information about things that happen, either like the operator took some notes, just arbitrary notes. They noticed something that somebody should look at, or things that were an issue, like the driver had to disengage because the vehicle was moving maybe too far to the edge, or he didn't know if it was going to react right to something that was happening. So those sort of get pulled out and cataloged. And we actually put those, we call them triage events, get put into Jira, which is it's kind of an abuse of Jira. We beat it up a lot, but it works really well because that ends up working nicely with the developer workflow and releases of the software, and we can say, okay, what issues are fixed, and they can group them together and create meta issues that are then sort of representative of how to reproduce the bug. So we have all this data. It's all cataloged and ready to go. What are we going to do with it? So I think about the data in a couple different ways, and I keep kind of rethinking about how I call these, but I think the one that works out best in my mind is we kind of work with the data in 2 ways. One is sort of message-oriented, where we just use the data as it was written by components that are maybe even the same components running offline. Like if we want to reproduce a problem, we can actually run most of the partial software stack. Maybe we're running the planner, and we feed it perception information from an actual drive. And the planner thinks it's in the car driving and it's making decisions. So we can use that as like for regression testing, or developers can use that to debug the problem on their machine. So, I mean, it's actually hard to debug, a problem in real time in a robot, but if you can reproduce it perfectly because you have the exact data that came into it, you could do that offline. Reproduce it, fix it, write a regression test, and never break it again. And then the other way we look at the data is sort of analytic. I think maybe an analytic way is a good way to call it, is like asking questions after the fact, or the data that is there but not really organized to answer your question specifically. We're not like writing a record that answers your question because you thought of the question later. So more like traditional data analytics, asking for business information, or other sort of metrics and measurements, performance things that might come later on, where you're aggregating across lots of data. So I'll go into a little more detail on these. So for the message data, this is like the bulk of our traffic. We basically keep that in the data center. It's still in the same chum form. We may move it into a different storage for our hot access data, and we make it co-located more closely available to the big compute clusters that we have. So we have effectively big supercomputer clusters, lots of racks of Linux boxes with stuff full of GPUs. So they're doing all sorts of things like machine learning and running all of our tests that are running and all the other things that need data. So some of the things we can do just by looking at some of the simple kind of meta messages that are on the bus having to do with, we can look at timing between messages. We can produce reports so that teams can look at, well, how fast are their components running? Are they kind of keeping up with their allotted tick time? Are they, the cadence, are they producing their output within the time window that they're supposed to? Performance, what kind of CPU? So once you can kind of correlate that, I think that's going to be the next slide, a little bit more detail on performance. But so you can look at a lot of information like directly plotted with some simple tools that a lot of the core, like our core team develops these tools. So just a quick look at some of the primordial messages that are being used all over the vehicle. Then we can also cross-reference some of the same timing information in the messages with behavior of like CPU, standard kind of CPU analysis and dumps, so that we can correlate CPU usage flame graphs with timing and delays and what was happening where, because it's like lots of cores are running, they're all doing different things, they're all sending messages. It's really tricky to debug that unless you have like really good tools to dig in and correlate like causality of what message was sent and what thing triggered maybe a big CPU spike in another component. And of course we use the data that we collect, so all of the data from the LiDAR especially, probably radar too and vision, are used to sort of aggregate together over lots and lots of recordings and build localization information. So using GPS and other systems combined with what we see, LiDAR, and averaging that out over a long process, we can create very, very accurate digital maps that tell us where things are exactly in line to each other within like a centimeter or two over the whole city area that we drive. And playback. So we can also take those messages that we recorded and play them back and effectively render them in different ways. And I'll run the movie in a second, but what you can see on the left is camera capture, but then with overlay that was put on there, where all the information for the overlay, like where the boxes were going to be in that space, what sensors, modalities picked up on the different agents, that was all recorded. All of the information for the 3D imagery on the right, all those agents and what kind they were and what all their plans were, those are also recorded and then overlaid on top of the map that we run on. So this is just one of our published little video montages showing what the vehicle's doing. And we can lay out these sort of video generations based on just what the teams need to build. So this is one we build up. It's mostly for us to show off, so it's fun to watch. We can see the pink agents are pedestrians, the blue agents are vehicles, and orange is bicycles or scooters. And on the right you can see the planner, so it shows on top kind of the signals indicating what the vehicle is intending to do. It's going around double parked cars. And on the bottom is the same, but it's the top view. And the red gate saying it knows it's going to stop there. And then the green lines are the prediction vectors coming out of every agent, so we know prediction of where we think the pedestrians or other drivers are going to go. Okay. And one of the things I mentioned earlier was like when something happened, a disengagement generally, the operator will have taken notes. The disengagement will be recorded in a message. We will bring that around gather that information and save that in Jira. And then the teams can take a look at the Jira tickets. QA might look at these first, or engineers might look at it right away and decide when you want to go look at it. So they have everything they need to know here, all the metadata they need to go out and grab the chum and reproduce the problem that occurred. And they can look at that. We can categorize it. We can ticket it. We can play it back and see what happened in different views, and we can generate sort of different looks. We have ways of laying out windows where you can watch what happens and look at metrics and timing of messages and all sorts of diagnostic information that happened at the same time. And we can save those and snip those off and turn them into tests that we run over and over and over again to validate things. We can also take those sort of log tests, so just tests based on real data, and sort of manually, partially automated, and manually sort of craft tests that are more synthetic that we can then use to reproduce this problem in the same way, but then add some additional fuzzing. So you can create, well, let's say, what if that pedestrian walked a little faster or a little slower or went to the right a little bit more? So we can then sort of expand, multiply out the cases that the particular test can test for. Yeah, and I think I already mentioned a lot of these. Developer debugging on their, having all of the data available for people to just debug things on their desktop or run them in the job, writing jobs in our job queue. Machine learning training, of course, and labeling for identifying things. And then finally, the last bit, I'll cover this just a little bit, is analytics. For a long time, we would just kind of run scripts and pull the data out of Chum and directly look at it with Python. So we can do analytics that way, and it works really well for kind of ad hoc queries. If an engineer wants to look at a lot of data and just pull out like little threads of information across lots of topics over a long period of time, they can do that using some nice Python analytics tools that we have, sort of direct access to the Chum data. But we wanted to kind of go more a little more formal. Let's leverage some of the tools that are out there for data analytics. So we now kind of proactively ETL a bunch of the Chum data that we found to be interesting and put it into a columnar store. So we're using Redshift now. Could be whatever works in the future. But given that we have this sort of common set of data that's very useful for lots of different work, we can get that into the columnar store on a regular basis, regular cadence on ingest, and then use it to produce all sorts of different kinds of reports. These are kind of intentionally blurred out a bit, but like the idea is it can tell us like how well we're doing on a particular route in San Francisco. Let's say we're driving a certain route that's challenging, and we want to say, well, how well are we doing on that this week? Each release over time, are we getting better? Or certain situations occur, jaywalkers or bicyclists like to run stop signs. Where do we find that? We can then sort of track that and gather that information out of the raw data and make it available and visualize it directly on maps. Great heat maps where things are. We can also use it to generate our DMV report that we have to do every year. And so that's basically it. Thank you.